Quantum computers use quantum mechanical phenomena to store and process information. Modern quantum computers currently leverage the principles of superposition and quantum entanglement to perform calculations. In the quantum world, superposition is the idea that one thing can exist as a combination of two or more things. For example, an electron's position is thought to exist in a quantum state. This means that within the electron's orbital the electron simultaneously exists all throughout its orbit. Superposition allows us to free computers from binary constraints. Instead of being in a definite state, we can apply a probability of being in any state. When two particles have dependent states, they are considered to be entangled. It occurs when a pair of particles, such as photons or electrons, interact physically. A laser beam fired through a certain type of crystal can cause individual photons to be split into pairs of entangled photons. Photons can be separated by a large distance, hundreds of miles or even more, and remain entangled. This principle is used to purposely entangle particles within a quantum computer.
Taking a step back, let's take a look at classical computing compared to quantum computing. In classical computing, a transistor is the simplest form of a data processor, which basically acts as a switch for either blocking or letting information through. This information is called a bit. It is the term used to represent information by computers. Information is processed as ones and zeros. Ones and zeros, a bit, like an atom, are the smallest unit of storage. Combinations of bits are used to represent more complex information. For example, 8 bits make up a byte, which is considered a unit of memory size. Combinations of transistors form various logic gates which perform simple functions. Combinations of logic gates form essential modules, like ones for addition and multiplication, which in essence make up basic operations of a computer. As technology is improving and transistors are decreasing in size, progress in classical computing is reaching a physical size barrier and limitation. To deal with this issue, quantum properties are used to build quantum computers. Quantum computing is not intended to replace classical computing. Rather, quantum computing is a tool intended to be used in applications in which it can be more effective. Examples include the following: machine learning, computer security, computational chemistry, code breaking, drug design, and various many more applications.
Bits can be seen as 0 or 1 in the real world, and only one of the 4 possible states can exist at any time in space. For quantum computing, all 4 possible states can coexist in time and space in a quantum superposition state. Increasing the number of bits in a computer allows a traditional computer to store more information. Increasing the number of qubits in a computer allows for a number to be read with more certainty.
In what applications does quantum computing excel compared to classical computing?
The amount of information stored in n qubits is 2 to the power of n classical bits. It is extremely faster than the classical computer.
What do quantum computers look like?
With new advances in this technology, everything is susceptible to bugs. This is why so much testing must be done. So, where do the challenges lie in quantum computing? To begin, it is an error-prone system. The fact that quantum computation is reliant on physics properties makes it susceptible to decoherence. Decoherence is when the system does not stay fully isolated from its environment. The wave function, or quantum state of a system, is lost to the environment. One solution to decoherence has been to create a magnetic field around the system to keep it isolated and prevent loss to the environment. Decoherence may be resolved, however, other issues remain. One of the neatest aspects of qubits becomes a source for error. The state of qubits can occasionally flip or randomize due to various factors such as heat in the qubits or within the fundamental quantum mechanical processes. It is amazing that qubits can change like this. However, even a minor change can drastically change an outcome. Errors from quantum flips have altered computations negatively. These challenges are being researched further every day. Although they will always arise, it will be exciting to see where quantum computing takes us.
What is the future of quantum computing?
We can expect to see quantum computers built to serve a specific purpose. These computers will have a relatively small amount of computing power but will be able to solve specific optimization problems better than any modern supercomputer. Today shipping companies have a mathematical inefficiency that is currently creating large inefficiencies in the shipping distribution chain. This inefficiency boils down to the exponential growth of possible routes as you add destinations that the delivery people need to visit. The amount of possible routes can be represented by the factorial of the number of destinations. This means that if you only have to deliver invitations to 4 of your friends, you would only have to calculate 24 routes and compare them. But if you are UPS and have to deliver an average of 15 million packages a day, you will have to compute around 10 to the million power different possibilities. With a quantum annealing computer the problem becomes much easier. Each qubit is oriented to represent a different possibility, then the computer finds the most efficient possibility all at once. This of course means that UPS may be waiting for a 16 million qubit computer to be able to solve their problem. But it is theoretically possible. Another type of quantum computer we may encounter in the future is an approximate universal quantum computer. These computers may contain between 1000 and 5000 qubits and be designed to outperform their traditional counterparts in a multitude of areas. The areas they will excel in include the following: optimization problems, quantum chemistry, material science, and quantum dynamics. The major goal of quantum computing researchers is to one day create a fault-tolerant universal quantum computer. These quantum computers would be universal just like their transistor-based counterparts. They would also be fault-tolerant, meaning their qubits would hold their positions over large amounts of time. There are currently massive engineering challenges that need to be overcome before this is possible. IBM, for example, has only been able to achieve 90 microseconds of state preservation with their 20-qubit machine and have only recently built a 50-qubit machine. A fault-tolerant universal quantum computer would need to hold their states for hours, days, months, or years, not microseconds, and would have to be composed of millions of qubits. But if the challenges are overcome, they would be able to bring forth a new era in the areas of cryptography, machine learning, quantum chemistry, quantum dynamics, and the development of new database search techniques.
Quantum computers have seen tremendous growth. Quantum computers have gone from having 5 qubits to 50 qubits in a little over a year.
We want to say thank you to our awesome team: Danny Tran, Sergey Zarubin, Derek Bodo, and Lacey Sykes. A special thank you to the following. Our video would not have been as smooth without them.